Welcome to session 4 of the optimization lecture. Now, up to this point, we've been talking about first and second derivatives, and we haven't talked about how to obtain those. You can, in much of Stata's optimization routines, provide Stata with the equations directly. So in your program code, you not only provide the equation for the function itself, but you provide the equation for the derivatives and the second derivatives. This can be somewhat laborious. And in my experience, it actually is typically not worth it because Stata's numeric derivatives actually work quite well, which is its default. And here are what the numeric derivatives are. Numeric derivatives are essentially taking the function at the current point, subtracting that from the function value at another point, dividing it by the difference between the 2 points. And what that's going to come out to be is you take the function at the current point, then you take the beta at its current point, add a little bit, evaluate the function, take the difference, and divide it by the delta that you had added to the beta. And you use some small delta, essentially at the machine tolerance is typically what would be used. So this is to get a very small change in the function relative to a very small change in its argument. Another way, called the central difference approach, is to take the current point that you were at, add a small amount, subtract a small amount, and then divide by 2 times that delta, and that will get you another representation of the derivatives. Again, you use delta that's small. The first one has a little less computation to it because you do not have to evaluate the function beyond where you currently have it evaluated twice, which here you do. And it makes very little difference which of the two that you use, but this is an alternative to the forward difference model, which is what we have up here. Numeric Hessian is very straightforward, similar to above. You just simply take the differences, but now the differences are with respect to the numeric derivatives. So think of the numeric derivatives, df, as your function, and you want the derivative of this df, and that would be a numeric Hessian, or the matrix of second derivatives. All right. So let's move on then to some other methods real quickly. These are Quasi-Newton methods. There's 2 very common ones, and Stata provides you with the ability to use both. One is the Davison-Fletcher-Powell, or DFP. The other one is Broyden-Fletcher, Goldfarb, and Shannon, the BFGS. These will use, instead of the Hessian, and instead of the approximate covariance matrix, or the BHHHH, this creates a matrix W, which is some function. I won't give you the details of the function, but some function of essentially the change in the derivative from the point that you are currently at to the point that you're going, or some small increment change. And so essentially it keeps track of how the derivative is changing as you Actually, it is from your current point to the previous point because it's keeping track of the changes that you've undergone. And then you use the sequence of points similar to our other functions above. You've got this matrix W that you've calculated, and you multiply it by the gradient, and that's how you update your current point to the new point. These are always better than steepest ascent approaches. They're going to take more steps than the Newton-Raphson, but they can actually be faster because the Newton-Raphson takes a lot more time to calculate, whereas these are keeping track of and building W as it goes along in a fashion that's computationally much quicker than having to evaluate your Hessian matrix that the Newton-Raphson does at each step. If you do use these 2 methods, and they really are worth trying out because they can really make things go quicker, it's best to end with a Newton-Raphson in order to get a better calculation of standard errors. Now, by ending with, what do I mean? Well, Fortunately, Stata allows you to alternate between different methods, and so you can tell it to use one method for a certain number of iterations, then switch to another method for another number of iterations and go back and forth. But also, once you've achieved the optimum, you can save those parameter values, and then you can run the same program again, starting at the solution, only now tell it to use the Newton-Raphson analysis. Now, it's going to be at the solution right in the one step, but now it will use the Newton-Raphson to be able to calculate the standard errors. Now let's look at some problems. These are some kind of general problems with nonlinear optimization. One is you can over and understep, as we had mentioned before, and this is due essentially to the what's called intrinsic curvature, or the role of the parameter space. And the solution to this was that we would vary our step sizes. So we would have a particular point that we are going to step to. It might go past the maximum, it might go a little bit short of the maximum. We will vary the delta and find out where the maximum along that vector is. There's another problem called parameter effects curvature. This one actually can give you some very serious problems. So think of this topological space, which is highly curved, as the parameter space that you're searching for the maximum on. Well, up at this end here, if you were to start, let's say, at this point, or over here, the quadratic curvature approximation might send you over to this point, but the curvature at this point might send you back over to this point. And what I'm saying is when it's a strongly curved space, you actually may end up iterating back and forth across the hilltop or across a valley if you're minimizing. And it may just keep on going. You may actually not converge to a solution in any reasonable time because it's bouncing back and forth and back and forth. Whereas if instead you were starting over here, you may simply bounce back and forth a couple times and then land on the optimum. And this has to do with the curvature in the parameter space when you're looking down on it, as opposed to the roll, which has to do more with the curvature associated as if you took a cross-sectional slice and looked across it. Well, what are the solutions? One, have good starting values. What do I mean by that? Well, it means you want to be close. This is closer to the beginning than this one, but close is a relative matter. It's kind of hard to say, depending on the scale, what close is. So, yes, you do want to have good starting values, but what is a good starting value is kind of hard to say. But by all means, it'll turn out with much of the problems that we deal with, you want to have good starting values. You want to be close as you can get to the optimum when you start. It's not quite as trivial as it sounds or as absurd, since if you knew where it was you were supposed to be close to, you would clearly just go to that point. But actually what it means is typically you find a simpler type of an algorithm that can get you in the ballpark, and then you feed those points as starting values into the more complex algorithm. As the class proceeds on, you will see how this works. Second, you can reparameterize. So just write the function in a different way, essentially, is the way to think of it. So the parameters are expressed in a different form. And that can help. Now, to know exactly how to reparameterize in complex functions is extremely difficult to do. But that is one possibility to try to solve this problem. Starting values actually is probably more feasible for complex functions. You just start at different values or have an informed way to get there using some other approximate type of analysis. But sometimes you can also figure out a way to reparameterize. We will talk about this in greater detail with one of the homeworks. Another problem is ill-conditioned Hessian matrix, the matrix of second derivatives, or the rate at which the slopes are changing. When we think of the Newton-Raphson approach, here is our second derivatives, and we take the inverse of it. I actually do a negative of that, but still we take the inverse of it. And one thing to notice then is if this is our h, and then we invert it, it turns out that if the diagonal, one of the diagonals on the Hessian matrix is considerably larger than one of the other diagonals, then it will be that the corresponding inverse of that is going to be considerably smaller than the corresponding component of the HTT. Well, what does that mean? Well, this is the rate at which the slope is changing. If this is small, that means that it's hardly changing values at all. The slope is just pretty much, it's kind of like you're on a really long, steady slope. If this is much larger, then this is a parameter that is actually being arrived at, let's say at some reasonable rate. This is the or I guess we're not doing our algorithm yet, but this is one where the information is considerable about that parameter because the slope is changing fairly quickly. But what does it mean in what you use? Notice it's the inverse of the Hessian that's of concern here, is that this will be a larger value. And therefore, your betas, as you change them and go to the next point, will actually be driven by the very points that are flat, rather than being concerned about those parameters that are actually we have information about. So our search is dominated essentially by the flattest portions of the parameter space. And in some way, this is kind of the opposite of what we would like. I mean, we're basically having no information about the parameter, and yet that's driving where and how we search for an optimum. So this is not a good thing if we have great differences in the matrix of second derivatives along the diagonal. If we look at the eigenvalues for the Hessian matrix, the eigenvalue actually is a measure of curvature in the direction of the eigenvector. And you can think of it actually then as giving you a measure of curvature along the components of different parameters in the parameter space. Not precisely, but pretty close to that in practical purposes here. So if we look at the ratio of the two eigenvalues, the largest to the smallest, this is giving us a sense of how much the curvature in this space differs across the different dimensions of our parameter space. And you want essentially the condition number to be approximately 1. Okay? And you definitely do not want it greater than 10 to the 15. And I'll explain why this is the case in another lecture. But at this point, this really is very bad for a number of reasons, but this is really what you're looking for. You're looking for them to be just about the same. That way, not one of them dominates the other when it comes to trying to search. So how can we do this? Well, one is to rescale the parameters or the data. In other words, this is relative, these are the derivatives, it's relative to the scale of the variables and the scale of the parameters. When you write your own code, you can simply rescale the parameters. Divide them by 10, multiply them by 100. And that can adjust the derivatives and the rate at which they change. You can respecify the model, which is to say maybe you have the wrong model, and that's why you have a poorly conditioned matrix. This is a question of just simply technical, the rescaling. This is an issue of it's actually a bad model. So the model that you've specified, the data can't inform. Rescaling will not help the second one. And similarly, you may just simply need more data. You don't have enough information. so that the model might have been appropriate, but you have aspects of the model that require more information than your data currently has. You need to collect more data. These two are essentially up to you. This one could be up to you, the rescaling. However, Stata will automatically do that, pretty much. In fact, you'll notice it in Stata's, say, maximum likelihood. You'll notice that it will, it'll mention a rescaling as it puts its output, as it's starting to search at the very beginning. And essentially what it's doing is it's trying to find a better scaling so that the Hessian matrix can be operational. They can search the space better and more effectively. And then they'll put it back, so to speak, when they report the results of the parameters. All right, so this is the end of this section. We will go on to one more section for the optimization lecture in a few moments if you move on to the next lecture.